Jacob, thank you very, very much for joining Energy Live News. I would like, of course, to start with the findings of your recent study. So how could NASA's James Webb Space Telescope spot alien civilizations based on the air pollution coming from their planets?
Yeah, the idea is that there's certain chemicals, certain molecules that we're putting in the atmosphere on Earth from industry. And so one thing that we look at in particular is CFCs, chlorofluorocarbons. And you may have heard of these because these are the ozone-destroying molecules that were banned by the Montreal Protocol a couple decades ago because of their role in destroying the ozone layer. And so these are things that were in products like Freon. They might be used to keep your air conditioner running. They're used in other industrial applications. And as far as we know, there's no biological way to make these apart from industry. So if we were to see chlorofluorocarbons or other kinds of unique atmospheric pollution in the atmosphere of an exoplanet with the James Webb Space Telescope, that would be really compelling evidence for alien technology.
Which was the objective, the initial objective of the study?
Our initial objective is to try to expand our conception of how we look for life on exoplanets. And so there's this idea of biosignatures. What is the signature or evidence of life that might be on another planet? And so we're extending that. We're saying like, well, one type of life is life that uses technology. Like us on Earth, humans are life just like other organisms, but we use technology, and our technology is starting to exert a signal that could be detectable at astronomical distances if someone was looking at us. So we were trying to kind of ask the reverse question. If we're looking for alien life out there in any forms, well, let's look for all kinds of biology, but what kinds of signatures might be unique to technology? And it's possible that the signs of technology might even be easier to notice than the signs of non-technological life.
So as I can understand, what your study suggests is that the telescope could search for industrial pollutants in the atmosphere of exoplanets. And of course, you focus more and specifically on chlorofluorocarbons, which were once widely used in refrigerators and insulating forms. Is that correct?
That's correct. And in our calculations, we specifically focus on the TRAPPIST-1 system. TRAPPIST-1 planet E is the best candidate to be a potentially habitable planet, maybe kind of like Earth, that might support life. We don't know yet, but it's at the right distance that it could support water. And this is a planet that will probably be studied by the James Webb Space Telescope, at least in some detail. Now, the James Webb Space Telescope will not be able to look for atmospheric pollution for planets around any star. So TRAPPIST-1e is a really good one. There might be a couple of others. But really, we're just at the cusp now in astronomy of being able to do this for other planets. So the James Webb Space Telescope is really exciting as the first time we have this capability. And so that just means the next generation of space telescopes may even have greater capabilities of really looking for alien pollution on a wider range of exoplanets.
I'm just wondering how sure you are that this specific air pollutant would be identified in these exoplanets.
That's a great question. Yeah, we're not necessarily sure at all that these, we studied 2 different chlorofluorocarbons, and there's many different ones even on Earth that we're aware of. So we studied the 2 that are the longest lived and the most potent greenhouse gases on Earth. That still doesn't mean that they're even the best ones for, if aliens are making these for whatever reason they have them. So really this was a demonstration of sort of a general argument that we need to be looking more at these industrial molecules that don't seem to be produced by other forms of biology. This was really just the first study of hopefully many more by us and others to look at, other chlorofluorocarbons. Halocarbons is the general class of molecules. Many of those are industrially produced. There's other artificial gases that are produced by industry and not anywhere else that could be useful for if you want to terraform a planet, you want to make Mars warmer, for example, on purpose, you could put some artificial greenhouse gases into the atmosphere. So there's a lot more work to be done. We don't know what the most likely candidate is, but what we do want to do is explore what are all the possibilities, what might be some evidence that a telescope like the James Webb would see of those kinds of molecules. And really, yeah, how do we then look at this more systematically so that we have a better framework for understanding technosignatures on exoplanets?
Are there any limitations that were identified through your study regarding the use of the telescope? I mean, the ability of the telescope that we'll have in spotting these pollutants. For example, in really bright planets, will the telescope be similarly able to identify these air pollutants?
Right. So the limitation has a lot to do with sort of the architecture of the James Webb Telescope, and how far away it could observe a system and still resolve the exoplanets around it. And so it sort of can't be too far away, but it can't be too close either. And so TRAPPIST-1 is at the right distance, and there's some other systems. So already with just the architecture of the James Webb Telescope, we're probably not going to be able to study more than one or two or a small handful of Earth-like planets that might even have this kind of life and maybe technology that we're looking for. The other technical point that's important to think about is what the James Webb gives us. You get lines that are little squiggles, and the squiggles will show dips, and where there's a dip, that shows that there's some molecule in the atmosphere that's absorbing sunlight, starlight, and the dips correspond to measurements that have been conducted in a laboratory about those molecules. So that's a little bit of the technical background. But the reason I say that is because you have to correspond the dips in the observations, in the wiggly lines, with specific molecules. And in this case, we're saying, oh, well, one of those molecules might be chlorofluorocarbons. But what if there's something else that has a wiggly dip at almost the same point as where it's chlorofluorocarbons? There could be wacky other things in the planet's atmosphere that might confuse us into thinking they're chlorofluorocarbons. So this idea that there's a false positive, how do you know that what you're looking at is what you think it is versus something else that's very similar to it? And so that's part of the work that has to be done too, is disentangling the real signals versus the false positives, so that when you have this data, you really understand what you're looking at.
In your study, you suggested that the telescope should be looking for dim, long-lived red dwarfs known as M-class star. Why is that? Does this have to do with the architecture, the design of the telescope itself?
That's right. Yeah. So we don't know where life is out there. Earth is around a yellow dwarf star, a G star, and maybe that's a common place for habitable and inhabited planets to be. We don't know. But what we do know is that the first place we're going to be able to search are the planets around these low mass red dwarf stars. That's mainly because the planets that are at that right habitable distance for liquid water to be on the surface for these low mass stars, they're closer into the star. And when they're closer into the star, it's easier to see the planets. So it's purely because these are the systems we're going to be studying soon with the James Webb Space Telescope and other ground-based observatories. That's the first place to look, so that's where we're looking. But yes, of course, it would be very exciting to then expand this search to planets around other types of stars, including stars like the Sun.
Jacob, my last question for you is that how optimistic you are that with this telescope, humans will be able to identify aliens in other, in exoplanets outside of the planet Earth, depending and based on data that we will get from the air pollution?
Well, I'll be honest, I'm not optimistic that the James Webb Space Telescope is going to be the one that definitively finds alien life. But I'm still really excited about it because I think it will be the first one to give us good data on what is in the atmosphere of at least one, if not a few more Earth-like extrasolar planets. Now that could reveal something that looks like alien life. So in the best case scenario though, let's say you find a planet, TRAPPIST-1e, it has water vapor and methane and oxygen, and then you see something that looks like chlorofluorocarbons. Okay, that'd be really exciting. But probably the data from the James Webb Space Telescope wouldn't be good enough that everybody would celebrate and pop the champagne and decide that we found alien life. It would mean that we have a lot more work to do to follow up on those observations with an even better telescope to really understand what we're seeing. So it could be exciting. We don't know how common life is out there. So maybe we find something like that with the James Webb Space Telescope. So it is exciting because it's the first time we're going to really be able to do that. But it's actually the next generation of telescopes after the James Webb Space Telescope that I'm most excited about, where we'll be able to study a larger number of hopefully nearby extrasolar planets and ask questions like, how common is water on Earth-like planets? How common is oxygen? Once we're starting to ask questions like that, then you're doing like real statistics with exoplanets. That'd be exciting. And we will have more than just one planet that maybe has a biosignature, but a lot to think about. So, it's going to be a while, unfortunately, before we find a definitive biosignature, technosignature in an exoplanet. But it's still really exciting because we're not going to find the answer unless we ask these questions and unless we build these telescopes. And the fact that this is a science question now and not just a pure philosophy question, I think is really exciting.
Jacob, thank you very, very much for your time. It was really a pleasure talking to you.